Hi. So now we are going to talk about the second application of Gauss law. And look at this. So here we are going to find out the electric field due to an infinitely large charged sheet. So how can you define an infinitely large charged sheet? So it's very easy to understand. And suppose I have let me see. So this is a charged sheet. So suppose you consider there are 4 sides, right? So 1, 2, 3, 4 sides. So if they are enlarging to infinity, that much big it is. So we can also say that, hypothetically we can say that sheet is gonna divide the entire universe into 2. So that is what is infinitely large. So it is beyond our imagination. You can think like that. Okay. So why I'm saying this? Because the point I'll explain after discussing this case. Okay. So second case, electric field due to infinitely large sheet. So a portion of the sheet, I have given a portion of that sheet, and here we are our first goal is we have to find out, or we have to identify the Gaussian surface. Okay. So the Gaussian surface, I have got the Gaussian surface, which is nothing but a cylinder. Okay. So in the last case also, in the case of infinitely large charged wire, we have seen that is a cylinder, but here it is also cylinder, but we are not going to consider this cylinder in that way. Okay. So here look at this. Here a portion of the cylinder, so it would be like this. So if this is a charge sheet, so it would be like this. Okay. So you can consider a cylinder in this way, and now the same method we will follow. The same method we have already done. The same method, that is what we are going to follow. So look at this. Here phi E is equal to, that is the electric flux due to this charged sheet is equal to surface integral E dot dA. That is what we already know, right? So which is equal to, so here in the previous case, do you remember that is the first top surface, and then cylindrical or curved surface, then bottom. So here also 3 surfaces are there. So look at this, 1 P, this circle, second Q, and this circle, and then that portion. Okay, that curved portion. So again I can write it is equal to the sum of integral E dot dA due to the cylinder or the curved surface plus sum of E dot dA, integral E dot dA at T, at surface T, and then at Q. Okay, now look at this, we have to check the direction, because if cos theta is equal to 0, then we don't have to consider that value, right? So look at this, here at P, let's consider at P. So here the direction of electric field, so look at this, it's a positive plane, it's a positive sheet, so the direction of the field will be in this direction, it is given. And what about area? The area vector direction will be also normal to that area, which is also same direction. So we can say that here theta will be equal to 0. Theta 0 degree. So I can say that this portion will be E into A. So I'll write it here, E into A. And what about at Q? So look at the point Q. So where is also E is in this direction and A is in the same direction. Both are in the same direction. So we can say that there is also theta is equal to 0, cos theta 1. So integral E dot dA will be equal to, E into A, or E into integral dA. You can consider it both way. E into integral dA. What about the cylindrical or curved surface? So look at the curved surface. It would be like this. Okay. So at this area, the aerial vector will be, or the normal vector to the area will be in this direction. What about field? Field will be in this direction. So they are at an angle of 90 degree. So look at this, electric field in this direction and aerial vector in this direction. Electric field in this area in this direction. So you can count any surface. You can count any surface, it will be normal. Okay. So that is why here the theta value is equal to, in this case, in this particular case, theta is equal to 90 degree. So that this value will be equal to 0. So you can neglect this value, we can take this value, this two. Okay, we can take these two. So in integral E dot dA, integral E dot dA. So the sum will be 2 into integral E dot dA. So I can write 2 into integral E dot dA, that is equal to Q enclosed divided by epsilon 0. So now only we have applied the Gauss law. Now only we have applied the Gauss theorem. Okay, the Gauss theorem. So it is very clear that 2 into E integral dA, which is equal to Q enclosed by epsilon 0. Now the same challenge we have already faced in the previous case. So we have to convert Q enclosed into the format. Okay, how much is Q enclosed? Look at this. Q enclosed will be equal to, so this is a sheet, and sigma will be the value. Sigma will be the value of what? The surface charge density. So surface charge density into total area, that will be the Q enclosed. So I can substitute the value here. So this value I have substituted here, 2EA. So integral dA, you can consider the total area A. Okay. So this is equal to sigma A divided by epsilon 0. A got cancelled. This is why I haven't given any other values to A. So I could have considered the area is equal to pi r square or whatever it is. Okay, but we don't have to consider that because this A is gonna cancel each other. Okay, so E is equal to sigma by 2 epsilon 0. This is what is our value. How much is E? Sigma upon 2 epsilon 0. Sigma by 2 epsilon 0. So this is what is sigma, surface charge density. So look at this. Let me give you an interesting fact. That is, suppose there is an infinitely large charged sheet. So the charge density is sigma only. So what will be the electric field? Suppose this is a charge sheet. Excuse me. So this is the charged sheet. So infinitely large. So you just assume that this is infinitely large. And what will be the electric field at this point? It will be. What will be the electric field at this point? This will be sigma by 2 epsilon 0. What about the electric field at this point? Sigma by 2 epsilon 0. What about here? Sigma by 2 epsilon 0. So it does not depend on what? The distance from the sheet. Why? Because it is infinitely large and charged sheet. And so that's why it can produce electric field, the same amount of electric field everywhere. Okay. And one more thing I would like to give you. That is, this infinitely large sheet is, this is hypothetical, right? But in practical applications, we can use the same theorem sigma by 2 epsilon 0 when, look at this, suppose this is a finite sheet, the size is finite only, and when we consider a small charge, a small point charge very near to the sheet, when we consider a small point charge very near to the sheet, then it will feel an electric field sigma by 2 epsilon 0. Why? Because compared to the size or the distance from the sheet, the size of the sheet is very large. So the charge will feel that it is an infinitely large sheet. So the same application we will discuss later. We have to do some problems on that. Okay. So that is what is, listen. Okay. That is what is the electric field due to infinitely large sheet. One more point. Listen. So in textbook, one example it is given. So we have to find out, there is one positive sheet, there is another negative sheet. They are like separated by some distance. And the question is, and it is given plus sigma and minus sigma, the values of what? The values of surface charge densities. Question is, there are 3 regions, 1, 2, 3. Find the electric field in each region. Find the electric field in each region. So one by one we will consider. First region. Okay, look at this. First of all, we have to consider the direction of electric field. Right? We know that the electric field due to a single sheet at any point will be sigma by 2 epsilon 0. But we have to consider the directions of electric field since there are 2 sheets. Okay. So first we will consider this sheet, A sheet. So it will be, look, which direction it will be? It will be in this direction. EA or E plus will be in this direction. Why? Because it's a positive sheet. It's a positive sheet. So electric field will be, it will move away from the positive sheet. And what about here? In this direction, because it's a negative sheet. So it moves towards the negative sheet. Here it moves away from the sheet. In the case of negative, it moves towards the sheet. So I can say that E plus, E minus, they are opposite in direction. So the value will be E plus minus E minus, which will be 0. Okay. And next one, what about in the direction, like in third? So here the direction will be in this direction. First one, that is E minus will be in this direction. E plus will be in this direction. Okay, E plus will be in this direction. So what will be the net value? E net will be equal to 0. Here also 0. Sigma by 2 epsilon 0 minus sigma by 2 epsilon 0, it will be 0. And what about here? Look at this region. In region 2, the direction here it is in this direction. What about here? The direction will be in this direction. You got the idea? Here, positive sheet. It moves away from the sheet. So in this direction, E plus in this direction. What about negative? This is also same direction. Why? It moves towards the sheet. So the total will be 2 into sigma. Here, in between that, that is equal to E is equal to sigma by 2 epsilon 0 plus sigma by 2 epsilon 0, that is sigma by epsilon 0. This is very important. The application of this we have to discuss later. So this is equal to sigma by 2 epsilon 0. Suppose when we take, that is the conclusion, I can say that when we take two infinite sheets, charged sheets, one is plus and one is minus, that is opposite polarities, equal but opposite, then there will not be any electric field outside. There will be only a proper electric field, sigma by epsilon 0, inside the sheets. Okay. So we will discuss the next application in the next video. Thank you.